Okay. All right, so here's what we're doing today. So we're not quite done with chapter 5C that is. So let me get that open. Let's go to Moodle. And we'll find it right there. Let me just move this aside. All right, here we go. All right, so 5C, as you know, is our discussion about, well, we did previously scientific notation, but right now the focus is on sequences. So we're not quite done with that. So we want to wrap that up today. And then we can start 6. Now, in the meantime, though, there is a third problem set for this chapter, which we haven't started yet. So let me get that open as well. And so since we'll be done today with chapter 5, we may as well do this problem set on Thursday. We don't want to forget what we've been learning. And also remember that this is excellent practice for the midterm when it eventually arrives. Not for a while, don't panic. It'll be a little longer before that, but it will be based exclusively on chapters 5 and 6. Okay, let's see what's going on here. Okay, all right, hold on. So as far as the problem sets go, let's take a quick peek at it. So there's a lot of exponents in here, as you can see. And by the way, I just want to point out that I'll read these very carefully because in some of these cases, there's a little slash, which represents division. So for example, this one, you're supposed to calculate 3 to the 4th divided by 3 squared, not times. So these others are pretty self-explanatory. We have scientific notation, and we have algebra with scientific notation, and then we have sequences. Okay, so this is a fairly long problem set. Oh my God, and there's also word problems. But remember, as always, our job is to simply figure out what kind of problem this is. And then once you understand that, the rest should fall right into place. Okay, so we'll do this one on Thursday. And just be prepared for it to take a while because you can see there's a lot of questions here. There's more than 50, but it's excellent, excellent practice. Okay. All right. Anyway, so in the meantime, we'll wrap up chapter 5C. We're not quite done with our sequences. In particular, I seem to remember that we didn't quite get very far in our geometric sequences, so we wouldn't want to do that again. And then when that's over, we'll go to 6. Okay, so let me get that open as well. And 6, basically, in a lot of ways, is an extension of 5. These are also concepts that are related to what we've been doing, but some of these you may have seen before, some of them maybe not, but it's all very useful. These are all fundamental properties of algebra and algebraic operations. Once we're done with this section, we'll be moving into something completely different in chapter 8. We'll discuss that when we get to that point. All right, so let's just take a look here. Now, just a quick reminder, there are 2 basic types of sequences, arithmetic and geometric. And what really separates the two is the pattern. For an arithmetic sequence, there's a constant difference between the terms. Like all 3 of these cases, you can see in the first case, the constant difference is 1. In the second case, the constant difference is 3. And in the third case, the constant difference is -1. Okay, in other words, that tells us how to go from one term to the next. Once we've established that a sequence is arithmetic, there are 2 formulas that we need to know. Number 1, the formula that lets us find a particular term in the sequence, all right, as opposed to simply counting them out, which you can always do. But if you need to find, for example, the 100th term, then counting them out starts to become less and less attractive compared to using this formula. So it's a good formula to know. And we also may want to understand or know how to calculate the first n terms in a sequence. In other words, not just the actual terms, but their sum. So if I wanted to know, for example, the sum of the first 5 terms, this is the formula that I'd use. Okay, so like for this one, you might recall this is clearly an arithmetic sequence because the common difference is 2. How do I figure out the sum of the first 5? Well, I can add them up, of course, but what if I don't want to do that? What if I have too many terms to add them up? So here's our formula. Now, in this case, we need to know the number of terms, n. We need to know the first term in the sequence, a1. And then in this case, we need the 5th term, which was 9. Let's go back to the original sequence. The 5th term is 9. So basically what you need is this number and this number, the 1st and the 5th, to plug into this formula. And then of course you multiply by n and you divide by 2, and you end up in this particular case with 25. Now, by the way, I just want to show you a quick example of why this works, okay? Let me just sneak this in here. You might say to yourself, well, that's a nice formula, but I want to know why this works. Let me show you an interesting case. Ooh, I shouldn't have done that. Hold on. Nope, hold on. I know what I need to do. Suppose that an arithmetic sequence and you'll see right away, of course, it's arithmetic. And we can see clearly that the common difference is 1, which means that this is clearly an arithmetic sequence. And suppose I said to you the following. What is the sum of the first 100 terms? Okay. All right, well, that's an interesting question. Now, we clearly do not want to sit here and add up 100 terms. So we can use our formula. And even though we don't know what the 100th term is, it should be clear from the pattern that we're seeing here that A1 is 1 and A100 is just 100. Okay, if we weren't sure, we could use our formula to prove that. But we've got A1 is 100. Oops, hold on. And A100 is 100. So I want to add them all up. Now, if I had to do this manually, one at a time, it could take all morning. And I'd probably make a mistake somewhere along the way. So this is not my first choice. But if you look at it very carefully, you'll see the logic behind this formula. So why don't we imagine that we took all 100 terms, the first 100 terms of this sequence, and started writing them out. 1, 2, 3, 4. Now, what are the last 4 terms, let's say? 97, 98, 99, and 100. Now, we don't need all of them because the pattern never changes. Okay, so you all agree that this is what our sequence looks like. So I'm going to do the following. What if I took the first and the last terms and I added them up? What if I take the second term and the second to last term? What if I do the same thing for the third and the third to the last? 3 plus 98 equals 101. I think you're starting to get the idea. And the same thing holds with 4 and 97. So in other words, by lining them up this way, we can see that there are 50 pairs of numbers each with a sum of 101. So therefore, the sum must be 50 times 101, which is 5,050. Now, if we bring back our formula, we'll start to say, hey, wait a minute. I think I'm getting the point of this. Oh, wait, sorry, my mistake. Let me write it in a slightly different way, because I want you to see the logic behind this. What I had wasn't wrong, but I want to write it like this. So the point of it is that this actually represents the number of pairs, and this is the sum for each pair. So that's the logic behind this formula. You see what I've done? This part, n over 2, is the number of pairs that we're creating. And then here within the parentheses is the sum for each pair. And so that's why this thing works. So now, in this case, at least, you might just say, well, you know, now that I've seen how this thing works, I really understand it. I get it. I know what's going on here. It's, you know, obviously at first, when you're learning new formulas, it's, you know, of course, you're going to memorize them and you learn how to use them. But eventually there comes a time when you want to understand them. Now, some of these formulas, you know, it would be a while before we can really and truly understand them. But for something like this, I'd like you to see this because it makes it easier to follow along what we're actually doing when we add up the sums of a sequence like this. Okay, so that way you have some insight that you didn't have before. All right, now we went on to geometric sequences. And this is the case where there's a common ratio between the terms, not difference, but ratio. So here, for example, every time I go to a new term, I'm doubling it from the previous one. So the common ratio is 2. In the second case, I'm tripling the numbers as I go along. And in the following case, I'm quintupling them as I go along. So that's how I know that these are geometric and not arithmetic. It's obvious right off the bat, these are not arithmetic. There's no common difference. In other words, go from 1 to 2 and then to 4. Already you can see we went +1, +2. Wait a minute, something's wrong already. So you can see it must be geometric. And you notice these geometric terms get big really fast. That's one of the big differences too. These can grow incredibly quickly. Now, I'd also like to point out, although we don't have any examples of that here, let me make up another one so you can see this. In this case, the common ratio is actually -2. Okay, you can have a negative common ratio. And if that happens, you'll notice that because the signs are alternating between positive and negative. And you can also have a ratio which is not even an integer. Let's say, for example, you have 1, a half, a quarter, a 16th, an eighth, a 16th. Here the common ratio is 1/2. And there's nothing to stop us from having a fractional common ratio. And while we're on the subject, let's try this one. In this case, we've got a really interesting one. The common ratio is a negative fraction. So these are all possible cases, although most of the examples that we'll be working with, you'll end up with an integer. It doesn't have to be positive, but it often is. Okay, and you know, you might run into some of these in practice, like you might remember from high school biology when you're learning about bacteria and how fast it grows. You might end up seeing its growth pattern following one of these sequences. Okay, now, here's the formula for finding a specific term in a geometric sequence. And you notice, you can tell right away, because there's an R in here rather than a D. Okay, that's a tip-off that this one involves geometric sequences. Okay, N is the same thing. It's the term you're looking for. A1 is the first term. R is what we will call the common ratio. And then finally, this is the so-called nth term. Oh, by the way, I just want to mention one more thing. Not every sequence is arithmetic or geometric, okay? There are many sequences that do not fall into either category, but we will not be encountering any of them in this class. Let's put it that way. But in practice, there are many sequences that do not follow either of these. They have rules of their own, like the Fibonacci sequence that we saw earlier. Okay. By the way, oh, you know what I forgot? I wanted to try this out on you. Let's step back here for a second to arithmetic sequences. I want to throw a tricky one at you and see how you react to it. All right, here we go. This is a semi-trick question. Is the sequence an arithmetic sequence? I'll call this a tricky example. So we're looking for a common difference now. Remember, arithmetic is common difference. So it's in this case, we want yes or no and why. Okay, so imagine this showing up on a test. No, it won't, but let's say it did. All right. So the answer is yes, because the common difference is 0. That's a possible answer. Yes, D can be 0. Okay, so therefore this qualifies as an arithmetic sequence, even though it's just all 5s. It's still technically an arithmetic sequence. Don't you just love special cases like this? And then while we're at it, let's do a tricky one for the geometric sequences. Tricky example. I like calling it that. That way you know that you should be paying extra attention to this one. Is the sequence let's see, what should I do with this one? Oh, you know what? I just realized I made it. No, this is good. This is fine. How do you like? Let's try this one. Okay. The answer is yes, because R equals 0. Okay, in other words, to go from one to the next, we're just simply continuously multiplying by 0. Okay. All right. Anyway, I thought I'd throw that in there just for the fun of it. Oh, you know what? Let me do one thing here. Let me quickly save this. You don't save things. You know what happens? The minute the computer senses that you've neglected to save something, it will find a way to crap out on you so that you lose everything. Okay, today's the 27th.
I have a question.
Yes, go ahead.
Well, the last one, the difference was 0, and this one, the difference is also 0. So are they both arithmetic and geometric?
That's a good point. Yes, it is. It technically qualifies as both because D is also 0. So you're absolutely right. This is one of those oddball cases where it can either be both. And that's a very good thing to notice, because the way we've defined sequences, this one actually qualifies as both because the difference is also 0. And yes, the one up here, same thing. You could imagine that I could call this a geometric sequence if I define the common ratio as 1. So both of these cases are both geometric and arithmetic sequences. Very unusual. It's almost never the case that it's both, but here are 2 examples where they are. So that's a very good catch. Very good. That means you'll probably get an A in the test because you're so observant. That's a very good point. All right, very good. So anyway, let's go on to the sums. So we understand how the ratios work. And we did a couple of examples, like here we looked for the 7th term. So if you're looking at AN equals A1 R to the n minus 1 power. So remember, well, first things first, we don't actually have the 7th term right in front of us. So we can either use our formula. Oh, actually, sorry. That's what we're trying to do. We're not summing. Okay. So we can do one of 2 things. We can use the formula, or we can just figure it out ourselves by continuously doubling. And that's fine, but let's use the formula. And
She'll probably give you one warning.
well, it just says what's the 7th term. It doesn't specifically say how to do it. So if it doesn't say, then you can feel free to use any technique that you like. All right, so A to the 7th is 64, whether you use the formula or whether you simply multiply it out. And you can, like I said, you can do either one. In fact, what you might want to do is use the formula and then write them out as a double check. All right, that's not a terrible idea. In fact, double checking, unless the time involved is ridiculous, you probably should always double check your results, especially on a test. It's always good to know at least 2 ways of doing any technique in math. All right, so all right, let's jump ahead. Now, this is the one I don't think we've gotten to yet, the sum. Now, clearly the sum formula is going to be a lot messier for a geometric sequence than for an arithmetic sequence. And there's nothing new here. I mean, you know all the
spray, okay.
anyway. So let's try one. Oops. All right, so here's our sequence. Let's copy this formula here. Now, clearly it's a geometric sequence. You can see for yourselves that every time I move one more term, I'm doubling it. And of course, we also know that A1 is 5. We're looking for, let's say that we're looking for the sum of the first 4. Okay, so therefore N is 4. Now, if you just add them up, it's pretty clear that this adds up to 75. So I already know in advance. But let's prove it with our formula. So I have 5, 1 minus. Now here you have to be careful. The exponent is inside of the parentheses. Don't get it out here somewhere. It's 1 minus 2 to the 4th all over 1 minus 2. So what you should probably do is evaluate it in stages. 2 to the 4th is 16. And then we'll have 5 times negative 15 over negative 1. Now, the negatives cancel. So 5 times 15 is simply 75. And that's it. We're done. Look how easy that was. But you have to be careful. All right, let's see if there's another one for us to do here. I mean, they're all the same. You just have to be, like I said, a little careful, because sometimes the answers can be very messy. You could end up, because they're geometric sequences, you could end up with a very bizarre fraction, for example, or a negative number. But as long as we're careful, we should always get the right answer. Oh, that was the only one. All right, let's make up another one. I think we could use the practice. Suppose that the sequence is Oh, let's see. And let's try to figure out the sum of the first 5 terms. Now, the formula says that what we're going to do is take A1 times 1 minus r to the n over 1 minus r. We don't even need to know the 5th term to use this formula. So A1 is the 3, and n is 5. And you can see that the common ratio, oh no, I'm sorry, I did something wrong here. Oops, let me fix this real fast. Sorry about that, everyone. It was, I missed the 9. All right, so yeah, 3, 9, 27, 81. Yeah, sorry about that. So A1 is 3. We don't need to know A5, but these are the 5 numbers that we need to add up. Now, if you want to take out your calculator and do this, that's fine. But let's use the formula. Oh, you know what I forgot to do? R is 3. Okay, so there's A1 is 3, but R is also 3. Here we go. All right, now we're getting somewhere. Now 3 to the 5th power, let's see, that's a big number. What is it? 243. Oh yeah, it's right there. Okay. So you've got 3 times minus 242 over 2. Let's see, that's so negative 726 over, oh no, I did something's, you know why? Because this is negative 2, sorry. 1 minus 3 is negative 2, much better. Okay, this is what, yeah, this is why you should always write your examples in advance. 363 I've got, okay. All right, so I'm going to take out my calculator and just double check that by adding them up. 3 plus 9 plus 27 plus 81 plus 243, 363, perfect. Okay, so you can confirm this just by adding them up, and you do in fact get 363. Beautiful. All right, so that's really all you need to say about sequences. So like I said, now you're ready to do the 3rd problem set from chapter 5. So I'd like you to do that for Thursday, and we'll go over it together as we always do. In the meantime, though, it's time for chapter 6. Now 5 was a long chapter. I mean, we've been working on this for a while. 6 is definitely shorter, but it has a lot of important ideas in it. And like I said, some of these you may have seen before. In fact, you probably have seen several of these before. So first, let me quickly save this. Okay. All right, so we're going to start out some very basic concepts. We're going to be working on simplifying expressions and evaluating them, okay? Often in practice, the evaluation is what we're really after. Like, for example, if we have a formula that helps us calculate the maximum profits that we can earn from selling a product, then we probably want to know the exact value. It's not enough to have some algebraic formulas. We really need to know the maximum output that we can produce and still maximize our profits. So we'll start with some basic concepts. These are just key terms. You know these. We just want to review them very quickly. A variable is just some quantity that can change, and we often use the letters X or Y to represent variables. Somehow along the way, along the years, X and Y came to be associated with variables. In retrospect, I mean, any one of the letters could have been used, but we're so used to it that we'll continue to use X and Y as our basic variables. Now, an algebraic expression in principle is any combination of variables, constants, which are just numbers, and algebraic operations. Now, by the way, it doesn't become an equation until you try to set it equal to some value or other, like 3x squared plus 9 is an expression. And it has the variable x. There's there's really three constants. The constants, all the numbers are constants, 2, 3, and 9. And then the only operation, well, we actually have two operations when you come right down to it. Exponentiation and addition. So because it has all these elements, this is known as an algebraic expression. But if I write it like this, then it becomes an equation. Because I've set it equal to some constant, which means I can now solve for the variables. Okay, so that's the difference, an expression versus an equation. Now, you often run into this term coefficient. Usually, a coefficient is a multiplier of some kind. Like, for example, the coefficient of 3x squared is 3. Okay, in other words, it's this number right here. That's my coefficient. Now, this 9 is not typically referred to as a coefficient. It's simply a constant. The coefficients normally refer to constants multiplied by some function of x. All right, now I'm not going to ask you to memorize this. I mean, I'm sure you already know these terms anyway, but it's good to review them. The test does not have vocabulary sections. Let's put it that way. Now, because x is a variable, we can now assign it values. All right, now here's another example. We have x squared plus 3xy plus 2y squared is an algebraic expression. This one has two variables, as you can see, and this type of thing is sometimes called a multivariate expression because it has at least two variables. If it only has one, it's called univariate. And you can see why uni, the prefix uni means one. Okay, now here's an interesting detail. For x squared, there's an implied coefficient of 1. It's not actually written there. It's understood that x squared and 1x squared are the same thing. Okay, I just want to remind you about that. The coefficient of this term is just 3. Because that's the constant that's multiplying by those variables. And 2y squared, 2 is the coefficient of 2y squared. That one's pretty straightforward. What about the exponents? Now, here's something else we want to review. I'll just sneak it in down here. These are clearly the exponents, but what about x and y? X has an implied exponent of 1 because x and x to the first power are the same thing. And I can say the same thing for y. Y has an implied coefficient, an implied exponent of 1. Okay, so just quick reminders now. Now that your memory has been refreshed, let's review our old friend, the distributive property. This is often used with algebraic expressions. And so let's take a peek at it. Now, specifically, we're talking about the distributive property of multiplication over addition. It's not the only case, but it's the one we see the most often. So here's an example. You have a constant out here, and this is what we call a binary expression. Because there are 2 elements in it, the bi means 2. And you're being asked to do this, multiply the 3 by both terms and add them up. Okay, so you'll end up with 3x plus 3 times 2y, which simplifies to 3x plus 6y. Now, with this distributive property, it's easy, and I mean easy, to make mistakes with negatives. You just have to watch out for them. It's like, look at this one, minus 4 times 2x, fine. Then we subtract minus 4 minus y. Okay, so we end up with negative 8x, but positive 4y, because you've got a negative times a negative. And that's the kind of thing it's easy to forget about. All right, but so far none of this is new, I don't think. It's just that you might be getting a little rusty, okay? It's like anything else you don't do all the time. Yeah, so in other words, we need to get a lot of math practice, because otherwise it's easy to forget it. Now, simplification. Now, we've been harping on this the whole semester. Simplify whenever possible. The same thing holds here. All right, so anywhere in math that you run into any kinds of expressions, you always want them to be as simple as possible. So with algebraic expressions, the way we typically simplify them is to combine what we call like terms. So just as a quick example, suppose I showed you this one. What do we do with this mess? Well, we've only got one x cubed term. Let's put it here. So we've got 2x squares. When you combine these, you get negative x squared. There's only one x. And then you've got 2 constants. Oh yeah, what do you know? Now they're the same thing, but I think you'll all agree this is a much more convenient form than the one on top. And also, if you notice, we write these in descending order of exponent. Okay, so in other words, the highest exponent is first, 3, then 2. Now here there's an implied 1. And with a constant, just a quick reminder, 5 is the same thing as 5x to the 0. So there's an implied exponent of 1 here, and there's an implied exponent of 0 here. So that's why we can say that these are going in descending order. And so this is what we would normally do. But you only can combine the so-called like terms. We have to have the same variable and the same exponent in order to do this. In other words, I can't combine these two because they have different exponents. All right, okay, so that was pretty straightforward. Now, here's another example. Now, this one is easy because all we have is the 2 x's in common. And what you're actually doing is you are essentially reversing the distributive property to write this as 3 minus 5 all times x, so that it's easier to see, plus 2, that this expression is itself nothing but minus 2x, which we'll see here. So you can see this is the simpler version, and which means the preferred version. Of course, it's preferred. Oops, sorry. I just want to give you time to catch up. Looks like we've got a couple more examples coming, so let's get some practice here. All right, let's try this one. Now here it's a little bit messier because there's two like terms involving x squared, and there's two like terms involving the x, and there's one constant. So we'll bring together the x squares. Remember, x squared is the same thing as 1 times x squared. And down here, remember, we can consolidate these two. So when the dust settles, we end up with 4x squared plus 6x plus 5. Okay. How about this one? Oh, it's getting even messier. No, not really, because we've only got two terms that are involved x cubed, two x squared terms, and one constant again. All right, so bring these together. Don't forget the negative. Bring these together. And don't forget there's an implicit 1 here for the exponent, the coefficient rather. And so when you combine all these, you've got minus 3x cubed plus 9x squared plus 3. Very good. All right, so that wasn't, it's a blast from the past, isn't it? You've done this before. Okay. Can everyone see what I'm doing? I just realized something's not right here. I can't see the names anymore. Oh boy. Wow, now that's pretty rough. I'll tell you what, I'm going to reboot that. Well, I'm going to get out of this and get back into it because now I don't know what's going on. Is anyone out there? Can you hear me?
Yeah, I see everything. It seems fine, but some people say they can't see.
All right, because you notice how, well, I don't know if you can see, I've got this little box here that shows me the names and it's all black. And this happened the other day and I'm getting very annoyed because I don't know what's causing this. And then if I reboot this, then we have to have multiple recordings, although that part seems to be working. I don't know what's going on here. So, the thing is, you should never depend on technology ever for anything. It always finds a way to let you down. And this is such a perfect example of this. So I'm just going to turn it off and back on again. And I hope that everyone will be able to see what I'm doing and I'll be able to see you. So let's stop for a minute. I'm going to have to turn this thing off. So even this bar up here that I'm supposed to be able to see is not even visible. So let me save this. Let me go. Very frustrating. Oh my God. Oh, here we go. Quit. I just had it. I just had it. No, it's not working. All right, I'll have to reboot the whole computer. All right, I'll be back in a few minutes.
Sounds good.